I'll start recording.
Okay, yeah, the projector is coming online and it's on.
Can you hear me properly, by the way? Okay, right. I'm just checking just because my laptop is a bit making some noise. So.
No, but it's okay. It's the sound is okay.
But so far, the strange thing, it's showing my desktop. Why?
It's showing your.
Oh well, because okay. The projector is showing, I guess, my desktop. One moment.
Yeah, you probably have two screens, so you can say mirror screen or something like that in the settings.
Doesn't the system connect directly to the tablet?
So the systems connect to the tablet, but then you are connected through the HDMI, so you are sharing the screen.
So I have to log into the Zoom.
No, you don't have to log in. So Zoom is in the tablet, but your screen is going through the HDMI. So you know what I mean. You have to share. You have to connect the laptop through the HDMI because the screen is shared through the HDMI. But you don't have to log in into Zoom in your computer because Zoom is managed by the tablet, by the operating system of the Polycom device.
Yes. Okay, that's
so now I can see a black screen.
Okay, now if I go to the Zoom, then if Ilin shares his monitor, right? Then he can essentially share. But I can't.
Yeah. Can you try to share screen, Ilin?
Yeah, sure. I'll do it. Well, okay. So it looks like you're already sharing your screen, someone else's screen, and I can't share. So someone else is sharing their screen, so I can't share. I don't know.
So it's me who is sharing screen. Okay, so Mohammed, take the tablet and click on stop sharing content.
So when I click compartir contenido, right? Contenido.
Exactly. So sorry, it's in Spanish.
Yes.
Yeah. Compartir contenido. So
Yeah.
if you say stop that.
Yes, dejar de compartir, right? Yes.
Dejar de compartir.
Yes.
Exactly. Okay, now Ilin, you should be
okay. Thanks.
Able to. I'm going to send the seminar reminder.
Okay, yes, your screen is full screen here. Yes, we see. Yes, perfect. We see your screen. You can make it full screen.
Yeah, just 1 second. I don't know why it's so slow. Okay, all right. Can you now see full screen?
Yes. Yes. Full screen on the project. Very nice. Okay, perfect. So I know almost all your collaborators except the last one are Ajaxen. It's great to
¿Qué tal el
Bien un poco, porque está conduciendo.
física con
Sí.
system, but it's working now, so I'm not gonna. I'm not gonna.
Sí, lo busqué el otro día y
Because we see the video
está
by
el
me
precio,
on
no está
the
permitidos
projector,
niños.
but it's not exactly on the corner.
It's
Ah.
not common. Oh, buena.
Por the weekend, para el fin de semana, dos noches, dos personas. Salía 700 euros y dije, bueno, eso pasa cada
Otra vez.
vez.
Pero la comida
Pero
tiene
ayer fuimos a
buena
comer.
pinta, guau.
Ayer fuimos a comer y era, vamos, tío,
Qué buena pinta, sí.
yo ahora, básicamente no como desde ayer. No comer. Ayer a las 7, ayer a la semana no tenía hambre, comí una tostadica. Esta mañana desayunado, ahora tengo hambre.
Y también nos invitaron mis padres a comer a un sitio espectacular en Peñíscola.
¡Ostras! Sí que yo voy a empezar a... Se empezó a morder.
Esa puntualidad británica. Exacto.
Testing the.
Try to see if the presentation's good. Does the presentation move?
Can you try going to the next slide? Coming back just to make sure everything moves.
Yeah. 1 second. Yeah, it was.
Yes, we see it. Yeah, we see it.
It's a bit slow though, but it was.
Could have been worse.
Yeah.
We can see the mouse, we can...
Yeah, we can see your
presentation.
mouse.
Okay, that's great. That's great.
Yeah, you can use that. Yeah, you're on Windows, right?
Did I get discovered?
Operating system for astronomers. But no, it's working good. Yeah, we see the transition smoothly. We see your mouse nicely. So everything is good. And you see the people, right, that are coming to see. So the camera's on.
Yes, I do. Yeah.
Hi there. I'm very interested in this topic, so I'll be very happy to hear from this research.
Yeah.
Nice. Yeah. Yeah, I'm looking forward to the discussion afterwards, to be fair. Like, it's really interesting topics.
Yeah, in fact, I told them about JPass and JPlus and how we can have narrowband information for some of these.
Yeah,
We probably have because they also use HSC, so it's in the north, and we must have some overlap with JPlus. So
Very
yeah, those narrowbands can probably have some interesting new insights.
Hola.
I didn't know Gareth moves to Korea. When did he move to Korea?
Yeah, he's in Korea now. He's found a job in Nottingham. He's gonna start in, I think, September or something. I cannot remember exactly, but maybe this summer. Yeah.
He was in Arizona before.
Yeah, he was before in Arizona.
Este usa es hablar. No, este creo que está.
So shall we start or shall we wait some more minutes? How many people? Someone missing?
In this floor, I guess most people are coming in. Yes. Yeah, I think we can start.
Okay.
Yes.
Okay. So,
Thank you.
hi everybody.
Sorry, Juan. Let me just let everyone know that you're being recorded also, your video, the audience.
Oh, really?
I don't know. Yeah, so yeah.
I need to know this with some time.
Maybe, I don't know, because the camera has
Yeah, those are
very,
easy.
very
It's okay, man. Yeah, so yeah.
Exactly. The first row, right of the column, you are out of the field of view.
Okay, so go ahead, Juan. Sorry.
Okay, so hi everybody, and thank you. Thank you for being here. We have today Ilin Lazar from the University of Hertfordshire. He's doing his PhD there. He has been working mostly with machine learning, and thanks to these techniques, he arrived to a very interesting scientific topic, which are these relaxed blue ellipticals. And that's all. Today he's going to give us the seminar about it, and thank you very much, Ilin. So you can start whenever you want.
Thank you, Juan. Thank you very much for the introduction, for inviting me to give this seminar. So yeah, as Juan said, I'm Ilin Lazar. I'm a PhD at the University of Hertfordshire, and my PhD topic is mainly aimed at developing unsupervised machine learning methods to distinguish between different morphological types of galaxies, especially aimed at future big data services such as LSST, Euclid, SKA. And so while we were using such an algorithm on the hyperspin CAM data, we've actually bumped into this interesting peculiar and rare objects that we call ellipticals. And by studying them, we were able to gather some evidence pointing towards the fact that accretion-driven stellar growth can be a key evolution channel for low-mass elliptical galaxies. And I'm doing this in collaboration with quite a numerous team in Hertfordshire, Korea, Paris, and Tucson, and Canada. So before I just gonna move a bit my, okay, yeah, thanks. So before I go into the actual results that we're interested in, I would like to make a brief introduction on why morphology is important for galaxy evolution, why is the key trace for galaxy evolution. So the main reason for that is that the morphological properties of a galaxy are characterized by the small and large scale processes that act on it or within its structure. These are of two types, internal, such as AGN, SNA feedback, or stellar biodynamics, or external, such as different types of mergers, ramp pressure stripping, or different types of gas accretion and depletion events. And there are many studies in the literature that actually point towards the fact that there is a strong correlation between this process and the formation of the Hubble types, especially for the intermediate and high mass regimes. And they also point towards a correlation between morphology and properties such as stellar mass, star formation rate, and local environment, which is mainly probed and shown in diagrams such as color mass and SFR mass relation, which I show in this slide. So these are some examples from some highly cited sources, where they basically show SFR mass relations and color mass relations for different types of environments, top high density environments, and the bottom panels are for the low density environments. And the main features here that we can see is that star forming these galaxies reside basically in the blue cloud and low density environments where they're able to basically keep their gas and maintain star formation, as opposed to the red spheroids, which are basically seen on the red sequence and are mostly present in dense environments, and they are quenched. Their star formation is quenched as a result of different merger and gas depletion events. But in this talk, I'll focus entirely on elliptical galaxies and their morphological transformation. So we know from many studies that the main driver for their morphological evolution is through strong gravitational torques caused by tidal interactions, and through basically the quenching of star formation and through the depletion of gas. So there are mainly this is of course mainly true for elliptical galaxies in the high mass regime and in dense regions of the cosmic web, such as nodes and filaments. And the main popular physical processes occurring that make this transformation are usually ground pressure stripping, starvation, strangulation, different types of galaxy harassment, which I will not be getting into details in this talk. So how can we visually see traces of these physical processes? What are the signposts of this phenomena? The answer is yes, we can actually visually inspect some images and actually draw some conclusions on their physical processes. And this is through tidal features, shells, stellar streams, kinematically decoupled cores, and many other tidal features. And to the right, we can see some examples from Kaviraj 2014 using Stripe 82 STSS data, where we can see shell around an elliptical and tidal disturbance around an S0 type. Of course, we have somewhat of a clear picture in the high mass regime, but what about the low mass regime? So although there are various studies of dwarf galaxies in the local group or very local universe, so ratios more than 0.01, 0.02, this information is quite sparse and quite debatable. And the main reason for that is that typical dwarfs with masses more than 10 to the 9.5 solar masses are actually not really bright enough to be seen outside our local neighborhoods, especially in past wide area surveys such as STSS, which are quite shallow. So then dwarfs in such surveys have actually extreme star formation rates and extremely blue colors. And for that reason, they actually impose a bias into any results that study the evolution of dwarf morphology. So, which is why these studies can be difficult. For that reason, we need observations of from deep and wide surveys. So, which is why there are various studies that actually study the evolution of dwarf ellipticals through their blue counterparts. So these are blue dwarf ellipticals. So these are basically just low mass objects with masses smaller than 9.5 solar masses, which basically resemble elliptical morphologies, but with colors and star formation rates found in late type galaxies. So star formation rates usually ranging between 0.1 and 10, 15 solar masses per year. And there are actually various studies of dwarf ellipticals that use dwarf ellipticals to infer evolutionary pathways of the dwarf elliptical population. And there is, of course, not really, so far there is not much consensus on their key evolutionary channels from the literature. And the main pathways that are discussed are through secular gas accretion, major and minor mergers, or some studies even say that they are both the key players. And these studies are mainly done using data obtained at very low redshift, so from gamma, galaxy mass assembly survey, and using, of course, also kinematic information. So, for example, we have the study from Murphy et al. 2019, which is actually quite popular among these kind of studies. Using gamma data and kinematic information, they actually find that about 65%, so about half of their sample is actually the rotation supported out of a sample of 60 objects. So you can see that these studies are actually based on really low really local universe, and they don't actually have too much statistics. So, and these are, of course, two of the main downsides, and the other one is that they actually have a lack of deep imaging that has basically not allowed for clear evolutionary picture on especially outside the local neighborhood regarding the evolution of this object. So in this study, so this study is actually that I'm presenting today is actually one of the first studies with the deepest optical imaging in a dwarf regime to date, and we are able to study this object using hypersupreme calm ultra deep DR3 images in the cosmosphere, which is about 1.5 degrees squared, reaching depths of about 28 magnitudes in GRI bands, so about 6 magnitudes deeper than SDSS. We use this in combination with the Cosmos 2020 catalog, which is just a catalog containing physical properties such as photometric redshift, stellar masses, transformation rates that were obtained using multiband photometry across 40 bands. I think, yeah, 40 bands from far ultraviolet to mid infrared. And they actually, just because of this variety of bands, they obtain sub% redshift errors for some of the brighter objects, and less than 5% errors with less than 5% for some of the faintest objects. So before I go into the actual results, I'd like to explain in more detail how we actually select our elliptical sample. So this is based on an unsupervised machine learning technique, which we actually use to separate from general morphologies. So statistic fitting, which we use to actually make sure that these objects are elliptical, and a star catalog using Gaia data, where we actually use to exclude any stars that can be contaminating our sample. So the first one to talk about is the unsupervised machine learning method used to distinguish between different morphological types. So this idea has basically been engineered in Hopkins et al. 2018, Martin et al. 2020, and which I'm actually currently also developing. This is graph clustering technique, whose feature space is basically based on the power spectrum of survey patches. So how the algorithm works is basically taking survey patches of about twice the PSF in size from galaxy images, and it's calculating the radial Fourier transform from that. You doing that, we actually obtain visual information on each patch, and then we obtain then we call the vectors obtained patch vectors. So we actually append all these patch vectors corresponding to each patch to data matrix, which corresponds to our initial feature space. This is then reduced in size using growing neural gas networks, which is just a technique of constructing a topological map. And this is just then the patches are actually clustered together to actually obtain clusters of the same patch type. So clusters with the same visual properties. Then we construct feature vectors using the histograms of patch types encoding visual properties for each object. So then we do k-means clustering on these histograms that correspond to each object to obtain morphological clusters for example, that define general morphologies such as ellipticals and spirals. And we label each cluster by doing a visual inspection of a small representative object sample. So here I show some examples of representative morphological representative samples from the morphological clusters, where we can see the algorithm can distinguish from the most general morphologies, such as spirals, ellipticals, the most detailed features such as H2 regions, high FG merges, and of course, this is to the left. We can see with the algorithm. To the left, we can see some results using the HSCDR2 deep data. But if you go to the right, this is using HSD candle data, which is, of course, got an increase in resolution, and we can see that there are even many other types of morphology in terms of central light concentration and colors. Just to explain in more detail how we got the initial samples. So before using the algorithm, we use two extended filters for stars. So from Cosmos 2020 and HSC catalogs, we use this algorithm on objects with redshifts smaller than 0.3 and all stellar masses, of course. And the reason why we do this is just because we want to actually achieve accurate classifications in terms of morphologies. Just because when you go to higher redshifts, you will get more fainter objects, and you will introduce an uncertainty, large uncertainty into the classifications of this algorithm. So these are the results that the algorithm is producing for HSCDR3 Cosmos, where it's able to distinguish between four general morphological classes. So that's just ellipticals, early type spirals with redder colors, late type spirals with bluer colors, and blue ellipticals, which is the topic of this talk. So the initial sample that is basically found by our initial political sample that is found by the algorithm is consists of about 1,000 blue S0, SA, and elliptical sources. The first thing we want to do is filter out any SA and S0 galaxies using simple component statistic treating on G-band images. So just because we want to make sure we actually filter all the elliptical galaxies, we use a searching index of 4 as the threshold, even though for dwarf galaxies, there are studies which point towards the fact that an index of 2 or even 3 is suitable to distinguish between elliptical and spiral morphologies. So the resulting sample basically contains blue ellipticals with high central concentrations, which were quite surprising to us. So then one can ask, could there be any more stars unaccounted for in our sample? So we wanted to be even more pedantic about this, and we wanted to do even further star filtering. So for that, we use Gaia DR2 catalog from Baylor Jones et al. 2019. which is containing object classifications for, I think, couple of thousand, or even I think couple of thousand objects between stars, classifications between stars, quasars, and galaxies. So by doing this, we can see that there is a correlation between the classifications in this catalog and the maximum residual values from the source secrets, where the maximum residual values for stars and quasars that are found in this catalog are actually significantly higher. So about one order of magnitude or even more than that, than the ones for galaxies. So I just to exemplify this, here I'm just showing some examples of source secrets from objects which have spectroscopic redshifts available to the left, and from objects which have been classified as stars in Baylor-Jones et al. 2019. And to the bottom left of the residuals panel, you can see these are actually the maximum residuals values. So we can see that when we click through left to right, we can see that there is a difference in about more than another magnitude in these values. So for that reason, we want to make use of the minimum of the maximum residual values among all the objects that are classified as stars, and that minimum is about 1.9 counts per pixel, to actually make separation between what's a galaxy and what's a star. But actually we use 1.5 counts per pixel just to be sure that we're making a good distinction. So just to recap, our final sample has been obtained from the initial sample found by the algorithm of about 1,000 blue SA spheroidal sources. Then we applied the two filters for disks and stars. So we apply sensitivity with index with an index higher than 4 and the maximum region value smaller than 1.5. Then the resulting sample is about 108 ellipticals, out of which 40 objects, so about 40% of the sample have spectroscopic object redshifts. So we know that they're actually galaxies. So this is a bird's eye view of the elliptical sample that we have, and we can see that these objects are quite unusual in terms the fact that in terms of their colors and their morphology, just because their morphology is actually quite smooth and featureless and diffuse as what you would see in a normal elliptical, but their colors and SFRs are similar as in late type galaxies. And first thing we want to do is look at their physical properties. So we find these objects about a median ratio of about 0.2 in our sample, and at a median stellar mass of about 10 to the 8.7 stellar masses, which actually overlaps the main distribution of the late type galaxies, and this feature has been found in work from Kanapan 2009, other highly cited work from the literature. And when we look at the color mass and specific star formation rate mass relations, we can see that the colors and SFRs are similar to the main sequence late type galaxies. But of course, they don't have the actual morphologies of the objects which they overlap, which are later galaxies. And this has been, of course, also seen in the past. So the main question here, now we know they have this enhanced star formation rates, and they have this weird morphologies, and in these extremely blue colors. So what drives this star formation activity? And one question that one may ask is it mergers? Are there any tidal features visible in the images? So out of 108 objects, we are finding only 3 objects actually have tidal features or mergers, so about 3% of our sample. And if we zoom into these objects, we can basically find a merger, an object with like a tidal disturbance, and an object with like a shell, which a tidal feature which looks like a shell forming. Yeah. So the next thing that we do, we actually look at the control sample of about the same number of random galaxies in the dwarf population from the cosmosphere, so same redshifts and stellar masses. And after visual inspection, we find that about 5% of these show a sense of interaction, as opposed to 3% as opposed to the interacting fraction in our elliptical sample, which is about 3%. So the interaction fraction in our elliptical sample is even lower than the interaction fraction of the general dwarf population. Furthermore, this is, of course, it's more likely to actually see tidal features when the galaxy is blue, just because the star formation has already started recently. So these evidence may point out that mergers are not actually preferential channel for their recent evolution, and this actually fits well with the picture drawn in Mahajan et al. 2018, where they actually, in their sample, they actually find rich neutral hydrogen in their structure, and they find that their elliptical sample, they actually reside in low density environments. So the likelihood of mergers in those environments is actually quite slim. So talking about environments, the next thing that we look at is we look at the location of these ellipticals in the cosmic web. So what is their proximity to dense points in the filamentary structure of the local universe? And we in order to do this, we use an algorithm called disperse, first engineered in Salisbury 2011. This is basically an algorithm that calculates the 3D projected local density and finds stationary points within that density field, such as nodes, filaments, and voids for a given redshift slice. And then by linking the local maxima, which are the nodes, and the local central points, we basically obtain something called a skeleton, which is just a network of large-scale filaments. So then we build the density maps for objects between redshifts of 0.18 and 0.3, using a redshift slice width of about 100 megaparsecs, resulting in 9 slices. And this is basically based on the median redshift error, which I'll talk in the next slide. And the other feature that we use to actually build the density maps is that we use galaxies with solar masses higher than 10 to the 10 solar masses. So the reason why we do that is that they actually trace very well the local gravitational potential and they actually have really low, they have lower uncertainties in their photometric redshifts. And to the left, I'm showing the median redshift role that we find as a function of redshift in the Cosmos field using the Cosmos 2020 catalog, and we can see that the uncertainties actually are quite large, if not double, for redshifts more than 0.2. And just because we wanted to make the study as accurate as possible, we chose the objects only between 0.2 and 0.3, with redshift slice width that's about twice the median redshift error between these rays, so about 100 megaparsecs. And to the right, we can see an example of what this sparse code has produced for certain redshift slice at about redshift 0.2. Where you can basically see the skeleton is drawn as the black line and the testicles as the color map. And we can, and here I'm overlaying all the general morphology such as ellipticals, spirals, and our elliptical sample. And just from a bird's eye view, you can probably see that the red ellipticals actually clump up very nicely in the high density environment, even though some of them are not, and I'll talk about that soon. And our elliptical sample on average looks like it's not actually they do not actually inhabit any high density environments, are actually really far away from the any filamentary structure. And we, of course, we wanted to make this make a more quantitative analysis on this. And to the left, I'm actually showing the distributions of our elliptical sample spirals and ellipticals for all the 9 redshift slices. So this is the distributions of the projected distance to the nearest filament, where I'm showing in vertical lines are just the medians of these distributions. So the first feature that we can notice here is that ellipticals reside indeed further away from nodes and large-scale filaments than their red counterparts. So we can notice that basically the peak of the distribution of the red counterparts is inhabiting the 0.3 megaparsecs region away from the nearest filaments, whereas the blue counterparts inhabit the 0.8 and 1.3 megaparsecs away from the filaments, region away from the filaments. And the other interesting thing is that we don't actually see immediate correlation between the different types and the local density distribution. And this may be because we're actually averaging these results across 9 redshift slices. So, and then each redshift slice may have obviously different density ranges. So we know that these objects are actually found in low density environments, so voids or outside filaments, and these are actually, and there are actually studies that show that this is actually the best scenario for circular gas accretion, as they basically dominate their environment. So there are actually no large galaxies or no large gravitational potentials that actually compete for those for the gas reservoirs that are actually available in those regions. So the main question that someone may ask, okay, so all these evidence points towards the fact that these objects, their key evolution channel is through gas accretion. But why don't we see any sort of disks forming around them? And one possible theory on this is that is the multiple stream accretion. So this is how this works. Is basically we have our elliptical, and this may have multiple accretion channels from multiple directions with low that come in at low angular momentum. And if you then average all that, you get a net angular momentum which is close to zero, which can turn into these morphologies. And of course, given their like really extreme colors, there is actually a study done by Song et al. 2021, where they basically look at the H1 at regions just outside filaments, and they actually show that these regions are dominated by small scale filaments, which we call tendrils. And tendrils can be a way of explaining this kind of motion of this kind of irregular accretion in those regions. So the last piece of evidence that we're bringing towards forward towards the fact that these objects can form through gas accretion is that we are actually we are looking at the mass growth percentage after 1 gigayear for these objects, and we can see that assuming a constant star formation rates over 1 gigayear, they basically have the potential to almost double their mass. And if we take this into account with the fact that the number ratio of blue ellipticals to red ellipticals for the same stellar mass and environments, so just outside the low filament region, this is about a factor of 2. And knowing that studies like Kaviraj et al. 2007 and Shavinsky et al. 2007, they actually find that a galaxy can actually move from the blue cloud to the red sequence over time scales of about 1.5 gigayears. It can be plausible that these objects are actually can be the progenitors for the low mass elliptical population. And so I just want to go to the summary slide now and outline the main results, and these are mainly so we find 5 main results. So we know we are finding that less than 3% of the elliptical sample show signs of tidal features. So the incidence of tidal features in the elliptical is a factor of about 2 lower than in the general population. They inhabit low density environments, so further away from stationary points such as nodes and filaments, which basically facilitates sustained and efficient gas accretion. So they're basically dominated the local environment. There are no high mass neighbors that actually can influence their accretion or that can provide any disruption in their accretion. So given and of course the last 2 points I think are pretty much one of the most important ones. So given their significant star formation rates, they actually have the potential to almost double their mass over the course of 1 gigayear, assuming constant star formation. So constant star formation rates. So and then the number of red ellipticals is a factor of 2 higher than the number of red ellipticals for the same mass ranges and environments. And given all these features, we can conclude that stellar mass growth by cyclical gas accretion can play an important role in the mass buildup of low mass ellipticals. and it is likely that ellipticals are the progenitors of their more massive red counterparts. And what we want to do in the future, of course, there's more to do about this. We want to look at the some spectroscopic data on this. So are they rotational or are they dispersion supported? How about the gas distribution around them? Look at some H1 data and gain more data from the from surveys like LSST to improve our statistics. And before I actually end, I just want to make some brief comments on some ongoing work, which is actually quite related to this. So we are actually working now on a sample of dwarfs in the local universe, so ratios of about more than 0.08. In the same Cosmos field is the same on Cosmos 2020 catalog, and by means of doing visual inspection, we're actually finding 3 general morphological types. These are elliptic galaxies, which contain the red counterparts and the blue counterparts. So we can see these galaxies even in the lower, even in the more local universes. It's been seen before in the literature. Later galaxies, where we actually even use Anshar masking to be sure that we actually do the right classifications, and we see any H2 regions or spiral arms that can signify some morphological properties for spirals. And of course, I should probably tell, if anyone wants to do any sort of classification in the dwarf regime, like Anshar masking is probably the best way of doing it in an accurate way. And the third class is what we find with such sort of a peculiar type. This is pancake-like type, where we can see that it's got this really featureless spot distribution, sort of like elliptical, but no central light concentration. So really low central light concentration. And my last slide, where we basically look at the restricting colors of the different dwarf morphological classes, and we compare with the massive galaxies. So we basically find that 70% of dwarf ETGs are blue, like the later galaxies. And when we transpose this information into the res frame colors versus log stellar mass space, and we plot some simple star populations with a look back time of 3 giga years, 4 and 10 giga years, we can see that the 3 giga year track actually follows quite nicely the blue cloud in which these blue ellipticals reside, and which also signifies that they are likely to have had some star formation in the last 3 giga years. For the last class, the more peculiar type that we found, so the pancake-like galaxies, basically we're finding that there is in the low mass dwarf band, so about 8.2 solar masses, and that may suggest that the formation becomes easier as the gravitational potential becomes more shallow. But of course, I think we need, even for that, we need more, we need kinematic information to actually see what's going on with this object. So this is the end of my talk, and I'll just leave you the summary. Thank you very much.
Okay, thank you very much. Any questions, Elena?
Thank you very much for your talk. Very nice. One of your main results is that the evolution of these galaxies is driven by circular gas accretion because they reside in low density environments. However, your density maps are built with a sample of galaxies with masses above 10 to the 10. which if I remember correctly, this is at least one order of magnitude more massive than the galaxies that you're actually studying. So did you check how robust your results are when you check that change that mass limit?
Yeah, so so this is a really good question. So the reason why we actually do why we build our density maps with galaxies over that have masses over 10 solar masses just because we just want to probe the general density of the cosmic web. And so when you go lower, when you build this spectrum of maps with like lower mass galaxies, you will actually introduce more uncertainty, not more uncertainty, you will actually produce more stationary points, and then you will have your results will become more uncertain just because you produce more filaments in your cosmic web. And we basically just wanted to trace the very general structure of the cosmic web. So I don't know if I answered correctly your question.
Yeah, more or less. So I guess you produce more uncertainties, right? If you decrease your mass limit. But I don't can say that these galaxies dominate their environment. You don't know how many galaxies of their similar mass are there around.
Yeah, sorry, I don't know. I just couldn't hear you properly. Just like I think you're.
So Elena was saying that if you don't know the galaxies with lower stellar mass that may be around these galaxies, then how strongly can you claim that they dominate their environment?
Okay, I see. Interesting question.
Just a comment. So.
Yeah, no, yeah. Yeah, good comment.
Something to consider for next papers. Okay, any more questions, Andres?
Nice talk. Thank you very much. I have two questions. The first one is rather technical. It's like, how do you choose the number of clusters when you use the CAMI? And then the second question is, have you completely ruled out that these galaxies were interacting with other larger galaxies? Because not all the interactions, not all the, like when you have a merger, yeah, you expect to have some features around the galaxy, but you can also have interactions with more massive halos that probably will just steer the stellar content. They can create an asteroid, but they wouldn't leave like a stellar stream or anything like that. And regarding these, I know you don't have the internal kinematics yet, but you do have the line of sight velocities for these galaxies, right? So I don't know if you have tried to, I don't know, compare these to nearby galaxies or something like that, whether you can, I mean, if you can comment something on that.
Yeah, we haven't done that yet. It's a really good thing to do next, actually, as well. Regarding your question about the, I think your first question about how did I choose the number of clusters when I used the k-means technique. So that's actually based, that was actually an iterative process where we used different numbers of clusters in the k-means clustering, and then we chose the ones with which had the highest silhouette scores. So it was just an iterative process. So yeah, I agree with you. So I think the best thing that we actually need for this to know more about this subject is just look at the line of sight velocities, of course, and of course when talking about so yeah, you're right. So we have not completely ruled out that, of course, you can have interactions and you cannot basically see them as tails or like see them clearly in real images. So I see your point. So
I have another question, and this is the last one. Have you had a look at the metallicities of these galaxies? Because
no,
the metallicity can tell you a lot about whether they were accreting gas or not, or stellar content or not, and what kind of gas they were accreting.
Yeah.
This could be
that's
something to take into account.
yeah, that's really good thing to take into account. Thanks. I'll do the next.
Thanks.
Yeah.
Just any more questions? Stephanie, then just loudly. So
Hi, thank you for your nice talk.
yeah, come here.
Hello, thanks for your nice talk. I have a question about your algorithm for classifying the galaxies. What percentage of your algorithm is reliable? Because in your paper, I saw a galaxy, it was elliptical, but you consider it as it was a spiral, sorry, but you consider it as a elliptical galaxy. And I want to know, you check it visually or not?
Yes, so we do visual classification. Just one second. Yeah, going back to this. So we basically obtain our morphological clusters at the end, and which of course they contain the objects with like similar visual properties, and we label. So we actually we classify each morphological cluster by using a representative sample from each morphological cluster. So morphological cluster can have between 10 and thousands of objects, right? And the way how we actually choose our representative sample that's being visually inspected is that we actually we take objects that are closer to the cluster node in the n-dimensional space, a sample of which, let's say 10, 20. Then another sample of 10, 20 objects which are just random distances from the cluster node, and another sample of 10, 20 objects which are the furthest away from that from the node, from the cluster node in the n-dimensional space. And that will give us non-biased pre-tested sample that's actually represent all the sample, all the cluster. So I don't know, is that clear? Or
If I can rephrase the question, maybe did you do a completeness and purity test in summary to make sure your true positives or false positives plot?
oh no, I mean you cannot really do that, just because you cannot do that for all the objects, just because this is an unsupervised technique. So we don't involve any labels. So if you see what I mean. So yeah, I don't know if I explained.
Well, but from an initial sample that you have, you should be able to, have a test set, right? That's what you usually do in the machine learning examples, right?
Yeah, but that's an unsupervised technique, so we don't have any labels, right? This is
And with other like visual classification, if you can, have you done a visual, like a random sampling of that of the classification, and then visually done a check to see how many of them are robust, let's say?
So yeah, I'm not sure I understand. So we are basically just doing the visual classification on on a sample from each morphological cluster. Like it's not, we don't do it for the whole. Yeah, I'm sorry, I'm not sure I understand.
Just to confirm, we just want to see if, yeah, how you can ensure the readers that this, this classification is, is complete.
I mean, we do that just visually.
Yeah. So if you, that would be a nice plot to add to convince, the users, the readers, let's say.
Okay, I wasn't sure how I can visualize, how I can do, okay.
Yeah, that's
Okay, I see what you mean. I understand what you mean. Yeah, just make a plot that actually shows that's complete. Yeah, I understand. Yeah, I haven't done it yet. Okay, you should. Yeah, I should do that.
So I also had one question, if there's no other questions from the audience. About those Gaia stars that you mentioned, to reject stars as one source of contamination, right? So Gaia is only complete up to magnitude about 20. But in HSC ultra deep, as you said, you go to 28. So how reliable, I mean, like for these galaxies, how useful is a Gaia catalog? Because it doesn't go much deeper than 20th magnitude.
So I mean, we actually did. Yeah, you're right about that. To be fair, we found. So we didn't actually have. So we used the Gaia catalog just as a way of making correlation between our maximum residual values and their classifications. But I understand that there is yeah, you're right. Okay.
Any more questions? I'm just curious, maybe let me just ask one more question, then I'll let everyone go. So the one with the graph, the method for the graph, the slide you had before, you had the random boxes over. So these are randomly placed, right, over each galaxy to get this topology, right?
Yes, I mean they're not randomly. They're not random. They're like spaced out in about in some length that we actually choose as corresponding to the PSF of the survey. So they're not completely random.
Okay. And do you consider the galaxy size? So do you put these? Do you place them within the footprint of the galaxy? Do you place them like within 2 times the crown radius or the Petrosian radius? I don't know, within a certain footprint size?
Yes. So we use the footprints. You actually use the HSC footprints that are given by the HSC pipeline.
The segmentation
just
map.
take exactly the data from the footprints, the objective field. Yeah.
Okay, great. Thanks a lot. This was a really interesting work, and there's a lot of nice things you can add to it. So I hope this was also useful for you. It was very interesting for us, the study. It was, thank you very much. And thank you very much, everyone, for coming. So let's thank you. Thank you. So, yes, thanks a lot for coming, Eileen.
So Mohammed, we were gonna actually talk to you about maybe getting that thematic information, right?
Do you see me now? Do you see me now? I don't see you.
Yeah.
Okay.
If you can like point us, what's the best instrument that we can use for this, like for getting the spectra for these objects, or what instrument should we use, or what can you say?
Yeah, so one thing we were thinking, and maybe it's related to the question that Andres was asking, the metallicity. So we have maybe I can share, let me join with my laptop,
Yeah.
And then I'll show you. So I have to, because right now it's this projection system that's connected to me. One moment. Okay. It's a really interesting topic. Very lots of we've chosen the right, really nice topic. So one moment, I'll get this in links again. So, so now, so we have, so I'll show you. I'll just avoid explaining too much to confuse you and then just bring the slides. So you bring the images. So I'll show like this. Okay, I should be. Oh, okay. So we're also live streaming now. We're still live streaming.
Okay.
So one moment. So maybe we can leave here and I'll send you a link.
Yeah, that'll be great. Yeah, thank you very much.
Then we can talk after this meeting.
Yeah, thank you.
Okay, so we'll finish this meeting here and I'll send you a link in a minute.
Thank you. Yeah.
Okay, see you. Bye bye.